Hello friends, today we will be discussing about the direct shear test and by which we can calculate the shear strength of our given sample, or we can say our soil. So let us just move towards the direct shear test. Before going into the main video, just make sure that you have subscribed to the channel and try to share this video with your friends so that they can also get benefited with this. Now directly we are moving towards the theoretical part. Now why we are using this and how we are using this, step by step we will learn everything. So in the theory part, we'll let us just know the strength of soil depends of its resistance to shearing stresses. It is made up by basically the components. First one is frictional and second one is cohesive. Now why frictional? Because due to friction between individual particles, we know that particles will have the friction among them, so they will produce some frictional value. And second one is cohesive. Cohesive means there will be some adhesion between the particles, they'll try to stick to each other, so which will create the cohesive value. And as we have discussed the Mohr-Coulomb's theory of shear strength before itself, if you have not seen that video, you can also check out that video. I'll provide the link in below section. So now here what they are saying that two components are combined in Coulomb's shear strength equation, which gives the equation as tau F is equal to C plus sigma F tan theta, where tau F is nothing but the shearing resistance of the soil at failure, C is the apparent cohesive of soil, and sigma F is nothing but the total normal stress on failure plane, and theta is the angle of shearing resistance of the soil. Now after the modification, the above equation has been changed. So let us just check out what they have modified in the equation. So the modified equation says tau F is equal to C dash plus sigma dash F tan alpha dash. So where C dash is nothing but the apparent cohesion of soil in terms of effective stresses. The effective word has been added and the effective part is taken in the equation. Then sigma dash F is nothing but the effective normal stress on failure plane, and the theta is the angle of shearing resistance of the soil in terms of effective stresses. Now if you want to calculate sigma dash F, so we can take it as sigma F minus mu F. Mu F is nothing but the pore water pressure on failure plane, because definitely there will be some amount of water sometime. So if we remove that, you will be getting your sigma dash F. Okay, now just let us just move towards the diagram, the figure, what it says and how the configuration of direct shear test is being done. So here we can see the direct shear test is conducted on a soil specimen and in a shear box which is split into two halves along a horizontal plane at its middle, as we can see in the diagram. Now the shear box is made of brass or gunmetal. It can be either one. Now it is either square or circular in plan. Okay, so it can be in both the shapes, in any one shape. Okay, so if you are talking about the square shape, a square box is taken as a size of 60 by 60 by 50 mm. Okay, so this type of size is commonly used in our labs. Now the box is divided horizontally in such a way that plane passes through the center. Okay, you can see the plane passes the sample at the center. Here the spacing screws are provided in both the sections and they are fixed to the upper half, and they are butt against the top of the lower half. Okay, we can see in both the section. Okay, and the box is provided with the gripper, or we can call it as grit plates, which are toothed and fitted inside it. Okay, inside the box. Now the gripper plates are plain, and for undrained test and the perforated for the drained test can be done in this type of direct test. Now porous stones are also placed at the top and the bottom of the specimen in drain test. Why we have provided pores? So that the water can easily drain out. Now if we talk about the lower half of the box, it is fitted to the base plate, which is rigidly held in position in a large container type of thing, and the large container is supported on the rollers. Okay, so rollers are not shown in the figure because it is hidden where the shaded lines are given. There the rollers are fitted. Now the container can be pushed forward at a constant rate by a geared jack, which works as a strain controller device, and the loading frame is used to support the large container. Now it has the arrangement of loading yoke and a lever system for applying the normal load. We can apply manually or by electric motor also, it can be provided. Now at the top they have provided a proving ring which is fitted to the upper half of the box to measure the shear force. Okay, so the shear force is only measured by the proving ring, and the proving ring butts against the fixed support. It is fixed against the fixed support. As the box moves, the proving ring records the shear force. Okay, so the shear displacement is measured with the dial gauge fitted on the container. Now another dial gauge is fitted to the top of the pressure pad to measure the change in the thickness of the specimen. If it is changing its thickness, definitely it will record your thickness measurements. Now the procedure we need to follow up is like, first thing which we need to do is check the inner dimension of the soil container and put the parts of the soil container together. Then we need to calculate the volume of the container, weigh the container in the weighing machine. Then place the soil in smooth layers. Okay, approximately 10 mm thick we can provide or place the layers of soil. If a dense sample is desired, then temp the soil. Then weigh the soil container and fill and find the weight of the soil. Calculate the density of soil. Okay, so first we calculated the container weight, then with the soil we have calculated the container. Then plane the top surface of the soil and put the upper grating stone and the loading block on top of the soil. Okay, so plane the surface, whatever ups and downs are there of the soil, plane it and then put the upper grating stones on top of it. Then measure the thickness of the soil specimen. Okay, now next step is to apply the desired normal load and remove the shear pin. Okay, so how much ever we need to require provide the load, we can provide the normal load. Then attach the dial gauge which measure the changes of the volume of your soil. Whatever sample you have taken, what we can do, just put the dial gauge and it will check the volume change, whatever volume change is done in your soil. Then record the initial reading of the dial gauge. Okay, you have to note down the initial value of your dial gauge and then calibration values. Then check all the adjustment to see that there is no connection between two parts except sand or soil. Then start the motor, take the reading of your shear force and volume changes till it's fail, and then you can add corresponding normal stresses and continue the experiment till the failure. Then record carefully all the readings, whatever you have noted or whatever is given, and set the dial gauges to 0 before starting the experiment. That we have done your that can be comes under your whatever measurements you need to take during your test. So these are the steps how we can calculate your direct shear test. So directly it is calculated, that's why it's known as direct shear test. Now let us just quickly see the merits and demerits of direct shear test. So in merit if you talk about, the sample preparation is very easy, there is nothing much big to do, so the test is very simple and convenient. And as the thickness of the sample is relatively small, the drainage is quick. Okay, and the pore pressure dissipates very rapidly, so it doesn't take much time because the thickness is very less. Now, it is ideally suitable for conducting drained test on cohesive soil. It is very easy to conduct on the cohesive type of soil, and the apparatus is relatively cheap. It is not so costly to find for your shear strength. It is easy to it is cheap and it is easy to use. Now, if we talk about the demerits of the test, the shear condition, the stress conditions are known only at failure. So before that, you will not be knowing any stress conditions. So it is a bit tricky, and the stress distribution on the failure plane is not uniform. It changes in the different stages. Then the area under the shear gradually decreases as the test progresses, but the corrected area cannot be determined, and therefore the original area is taken for the computation of stresses. So we can say that this is a demerit. Then the orientation of the failure plane is fixed. So this plane may not be the weakest plane. So we cannot say whether it's correct or not. Then the control on the drainage condition is very difficult because consequently only the drain test can be conducted on your this type of test. Then the measurement of pore water pressure is not possible in this test, and the side walls of the shear box causes the lateral resistance on the specimen and do not allow to deform laterally. Okay, so these are a few demerits and merits of this test. In next videos, we will be seeing the different other tests conducted by your shear strengths. So thanks for watching. Make sure you watch all the relative videos. Thank you.